Hello everybody, this is Matt Barco. I'm doing my project on exploring implicitly defined curves. So what I am going to do here is basically, I can't really use this program to do it because it doesn't have a built-in ability to do implicitly defined curves. There is a workaround to it. It's something called the zeros function. So if you want to define, I'm in the function window right now, so if you want to define a function implicitly, like, okay, zeros. So you see how it changed it there because this is a real function that it can deal with. So let's do an implicit thing that we know, like a circle. So x squared plus y squared. Oops, I've messed that up, so I gotta back up here. Delete. Alright, and then do that. So x squared plus y squared minus the radius squared. 25, let's say, equals 0. Where's equals at? Still getting used to this thing. Well, we don't need to do the equal 0 actually. Let's just make that our curve because we're trying to find the zeros of it. And for some reason you need this comma y to make it work. Right? So it's going to think about it for a second, and then it's going to, well, didn't take any time at all because it was on the computer. If you actually did that on your calculator, it would take it a little longer. And you can see how it struggles drawing it a little bit, but okay. So there is a way to get the cast on a TI-89 or a TI Inspire cast to do it, but I'm going to end up using Wolfram Alpha instead because, I mean, take a look at this implicitly defined function. This is the one that I would give the students to do, to play around with. So y squared minus 2x squared times x plus 8 equals c. Now that c is sort of going to be this parameter we play with, so I'm not going to put it in there. But it would normally be multiplied on the outside of this thing. Y plus 1, oops, it's supposed to be that. So y plus 1 squared times y, hopefully that works, plus 9. I'll put a little times in there just in case. It would have figured it out, but whatever. Minus x squared. Okay, so that, and then there would have been a little c right here. And we would have played around with the c to see how changing c changes the curve. But the only way that we could put that function into here would be to set one of these to 0. So let's just do the simple case where c is 1. So we don't need the brackets or anything. And then we just subtract all this stuff off. So what it would really be is minus y squared plus 2x squared times x plus 8. Right? And then this side would be 0. That's the same thing when c is 1. So let's put this stuff right here into the zeros function of the calculator and see what it does. Let's see if I can undo any of that. No, I can't. So I'll take a look at what this does after I do this. So let's go back and redefine f. So I got to go menu, graph, function. And I don't want to do a new one. I want to change this one. So, okay, I'm just going to use the keyboard if you don't mind. So, it's going to be all that stuff that I have over in the Wolfram Alpha window over there. So, y plus 1 squared times y plus 9, close that, minus x squared, okay, minus y squared plus 2x squared, oops, times x plus 8. So times x plus 8 close. Now hopefully this should be right. Okay, it went. It's trying to do it now. Okay. You see what it's doing here? It's messing it up. It's graphing this part. It's got this part right here, which is actually correct. We could try zooming out. So I'm going to go to, I guess, menu, view, no, window. Let's zoom out a little bit. So what's my center? I guess that's what it'll be. So it doesn't make any difference to zoom out. You can see how it's crossing there a little bit. That is what it's supposed to do. Well, let's compare this output to what Wolfram Alpha does. So hopefully if I just hit enter, this thing should do it. Okay, so it's coming up with a bunch of crazy calculations. Now, that's what it should look like. Okay, it's got the little hole thing there, right? But the rest of it, it's screwing it up. So we can't really use the cast to do this because of its lack of a built-in function for it. So I'm just going to forget about this thing here because it's just not helping us. I don't care. So I want to make this bigger. I hope that does it. I don't know how to use a Mac, so I'm just going to do that. Okay. Maybe that button. Well, anyway, the whole point of this is to see what happens when we change C. So let me get back to the way I had this thing set up originally. And what we want to do is overlap some of these things with different values of C and investigate how changing C changes the family. Because that C gives us a whole family of these things. So I want to go back to this. Y squared, maybe it'll have it in here. Minus 2. That thing right there. Is that it? No. Minus 2x squared x plus 8. Okay, y squared minus 2x squared x plus 8 equals, now there would be a c here, and then a y plus 1 squared times y. Now I didn't just make this crazy thing up. I got this out of a textbook that I was planning on using for that syllabus we had to do. So this is a problem actually made up by Stuart and his friends. Now I'm not sure what would happen right now if I just pressed enter with that C there. I think it would treat it as a variable. So let me make C to be something like 2. Let's see what it is when it's 0. Then it's just going to set the whole right hand side to 0, I guess. Okay, that's no good. So let's just actually make C 0. Okay. Ooh, look at that. So that's what happens when C is 0. All right. Let's see what I got here. So what the book suggested doing is graph the curves with C equals 0 and C equals 2 and figure out how many points of intersection there are. So that's what it looks like when C is 2. Let's just see separately what it looks like when C is 0. This is what it looks like when C is 2. Okay, that's the familiar one. So now let's see what their intersection would look like. So I have to have both of these things up here simultaneously, but it's easy to do. All I have to do, see, the advantage of working in Wolfram Alpha is that you have this mouse functionality. So I just, oh, come on, paste. Don't tell me you can't paste on one of these computers. That would not be good. I'm used to using a Windows machine. Okay, copy. Don't erase my comma. Dude, don't erase my comma. Alright, whatever. I'll put the comma in myself. Alright, So I don't want to have the same function. I want one of these to be 0. So let's make one of them 0. Now I believe this will actually draw both curves. Yeah, it did. That's not cool. Okay. Wow. So the great thing about Wolfram Alpha is that it zooms right in on all the interesting spots. It appears that there are points of intersection here. Yeah, it's just. I mean, there's clearly some kind of pattern going on there. I also want to see what happens when we put 1 up there. You know, really, the students would sort of be free to explore this as long as. I mean, I would obviously need to show them how to do. I've already got something in there. So, is there a paste button on this? There's got. Okay, was it command? Oh, command V. Okay. So I've got 0 and 2 up there. Let's make it 1. So I don't need this. Now it should draw all 3. I think it will. It did. Okay. So clearly there is a pattern. And this is the whole point of the exercise, is that the students can see what's changing here and what is staying the same. Now, look around over here. Okay, you can see that those little circle parts, because remember they were right on the axis, and they're not drawing the axes here, but there was those weird circles there, and so they're there. These points of intersection are sort of staying the same. So we could conjecture that if we put, one with a 3 up there, it'll intersect at these points, and there'll be another circle thing over there. So why don't we just do that? I don't know if there's some limit to how big this expression in here can be. I'm assuming there is. But it took that so far anyway. Let's make this a 3. Well, the book suggests making it a 5 and a 10. So let's do that. Let's get the 4 they suggest are 0, 2, 5, and 10. So what do we have over here? We have 0, then we have 2. So this next one, I think I made it 1. So I'm going to make this 5. And then this last one I put in, I'll make 10. Okay? So let's graph all 4 of them and just see what's happening. Whereas I believe it'll cross the same spot in all of those. Wolfram Alpha is fantastic for doing this kind of stuff. Yeah, look at that. Okay, so the green one clearly is the one with the 10 coefficient on it, and it shows you down here. It's got them all color coded and everything. So this is far better to do on Wolfram Alpha than it would be on the TI-80 or the TI-Inspire. All right, so you've got these crazy circle things happening every single time, and it looks like this little wavy part wants to go and touch the circle. So if we made the coefficient big enough, something would happen. Those two would hit each other, and I don't even know what would happen, but there is certainly one way to find out. Let's see. He went 0, 2, 5, 10. How about 20? I just want to see. I'm curious. There, but I want that to be a 20. This thing's probably going to start getting angry with me if I do too many of these at one time. But it appears to be doing it. It is. Okay, yep, look, it crossed. Ooh, and it waved around. As soon as it hit the circle, it sort of looped around. But yeah, see, it's consistently hitting these same points. So I think the students would actually find this stuff pretty fascinating, because I myself do. Seeing what happens when we do that. The book suggested another type of function that we explore, so let's get rid of these ones. We get the idea with these. I'm going to do x squared, a simpler one now, plus y squared. Maybe we should have done a simple one first, but this is the order the book did it in, so that's how I'm going to do it. And then the number we're going to be playing around with goes here, and then this x squared, y squared. Okay, and then equals 1. Did I ever try it with a c in there? I don't know. Let's see what happens. Yeah, I figured it wouldn't graph anything because it would think it was 3-dimensional. Okay, so that's supposed to be just a constant. So we can play around with this number. We might as well just put it in parentheses. Okay, so basically the students are going to be asked a more general question at this point. How does the graph of this thing change as C changes? So I'm not going to give them any values of C. I'm just going to let them do it on their own. So I'm going to pretend I'm one of them, and I'm going to try 1. Okay, ooh, look at that thing. Get away. I don't care. My brain just got brighter. Wow, that thing kind of looks like a, what is that? I've seen that before. But anyway, so this is the implicitly defined curve when you do this. Now you can factor out y squared or x squared and then do the division and solve for y. And you could sort of get a handle on what that function is, but I think that thing looks pretty cool. So let's try it when y is, or c is 2. I'm just interested in what's changing here. It didn't look like a whole lot changed there. Okay, let's make c pretty large. Oh, okay. So it looks like the sides of this thing are collapsing. Let's make C really, really large. Now I'm guessing they'll be really squished in. Yep. Okay. So hopefully the students would be able to do this, and there's no reason why we have to choose positive integers. You could do negative integers, and in fact, the book suggests that we let C be -1. Let's see what happens. Now let's just try to conjecture what would happen here. If this were -1, then look, we could factor out a y squared from this, and we would have, in here we would have 1 minus x squared. And so we could subtract x squared over here, and then we'd have 1 minus x squared over there, divide by 1 minus x squared, and we would in fact get 1. So we would have y squared equals 1, so y equals plus or minus 1. And simultaneously, you would have x equals plus or minus 1 by the same logic. So what we would expect is some vertical and horizontal lines making a square with points where the 4 corners of the square would be like 1, 1, -1, 1, -1, -1, and -1, 1. But let's verify that. Hopefully this works. Yeah, worked like a charm. So obviously the students might not be able to just see that right away. But, you know, then I could ask them at this point, that's what you're seeing. Can you now interpret what you're seeing? And can you prove that what you're seeing is correct? So it's a little bit open-ended. So really at this point it would kind of bring the activity to a close. I mean, let's just try some other numbers, just for fun. We could try overlapping them, but I mean, we could already see what the pattern is. Ooh, look at that. I don't like you. So I wish there was like a slider I could pull here and this thing would just react automatically. I could enable interactivity, but then I'd have to pay money, which I don't have for obvious reasons. But anyway, that is the project, and I hope you enjoyed it. I sure did. Bye, everybody.